Hi everyone. In this video, I will explain the properties module for the physical properties and in definition, I think that this custom definition and random variable definition is remaining. Um, but anyways, I will cover that in a detailed way. At this moment, let's just start with the properties and in the properties, let's check which one is the first one. So, in the material and in the absorbed boundary conditions, this is the agenda to uh, consider and discuss in this region. Um, so, in the absorbing boundary conditions, we have 2D material absorbing boundary condition and 3D material absorbing boundary conditions here. So let's first go to the 2D material boundary condition and let's define it for the soil domain, right? Uh, ABC's 2D soil domain, right? And here we need to define the thickness of the soil domain and the shear modulus as well as the density of the soil. So for shear modulus, if you have Poisson ratio and you have modulus of elasticity, then you can um calculate this from engineering mechanics equations, um, and it's not difficult. It's just a simple equation that is G is equal to E into 2 into 1 plus nu. So let's say that the shear modulus for the side is 2653.5 MPa. The Poisson ratio, let's say, is 0.18, and the mass density of the side is, let's say, we consider in ton per mm cube. So let's say 2.13 E minus 9, and let's say the thickness of the side domain is 10 meter. So you can decide this by yourself, and you can do it like this. And then after cloning, um, edit it and call it ABC's 3D soil, and let's convert this to 3D soil domain. So again, for example, if I consider it for the previous value 2635.5, 0.18, and mass density, let's say 2.13 E minus 9. And since it is 3D, it does not require any thickness considerations here. So that's okay. So now I have these two style definitions for the infinite elements, and in the physical properties, the next section, and then we have to discuss about these SDR concrete 3D, damage 3D, TC 3D, isotropic damage 2D, and orthotropic material, then randomized material wrapper. And then I will switch to them one by one to see what is present in this model environment here. Then we will switch to the sections and so on to continue this discussion here. So let's jump into the theoretical background of the absorbing boundary conditions. So this link is explaining it very well in the OpenSees documentation. So this is the link which is responsible for the discussion on it. So normally we have the acceleration magnitude and the source is defined in 2D as well as in 3D boundary conditions. So that take care of the uh, waves to observe in the analysis. So this command that we are discussing right now is uh, about how the OpenSeas is handling these through STKO. So this command that we are using here, this basically construct in observing boundary conditions for 2D and 3D elements, and the the definition involved between this 2D and 3D element definition is like this. For example, if we consider this, so this 2D boundary condition and 3D boundary conditions that we are using in this object for the physical properties. This basically take care of the waves that are present in the model. For example, if we have an analysis for a building that is something like this, right? And there is a soil domain here, which let me do in the blue color, right? And, and we want to introduce some seismic waves or some seismic excitation, for example. So this spring and dash parts are assigned to it just like it is present here, and this is incorporated in the uh, um, elements for 2D and 3D analysis. So the concept is something like this. For example, if I define it like this, right? So what is happening is, if, for example, a seismic excitation is produced in this direction in 2D, right? A seismic load is applied here, and this is some sort of height h for the building, and we want to get the performance of this building and see how the soil will observe here. We need to define these elements here. So for 2D analysis, we will do this by using this as a 10 boundary element here, and this will be done in this way. If a partition is created, and then after the creation of that partition, the properties is assigned to it. So if we do it for the observing boundary condition 2D, then this needed to be assigned to this region, right? And it is a four-noded quadratic element, something like this: one, two, three, and four. Right? One, two, three, and four. And this quadratic boundary condition that we are using here, for 3D we will have a 8-noded hexahedron element. So it, it is a break element, and if you are any other finite element analysis user, for example Abacus or any other software, you will be able to understand this nomenclature, right? So this is something which is very important in the analysis, and the main purpose is to uh, observe these waves that are generating in this direction, and they does not reflect back here, right? this side. The reason is um, there's an extra layer at the boundaries of the soil domain, and it take care of the wave reflection which typically arise with fixed boundary conditions. If you are using a fixed boundary condition at certain points, which means that this is an ideal fixed region, right? Sometimes it's done here. For example, if you are doing a model in the lab and you apply the boundary condition here, so this if a wave is generated, it will reflect back and it will not represent the real scenario in your structure. Even though if you are using a very large side domain, for example, if I have a mid-rise story building, right, and it has some stories here, and those stories, for example, this is a building here, and this is something like this, that this is the soil domain on which this building is lying, and let's say this is the base of the building for the soil, and we have this soil domain here. So if I define a fixed boundary condition at this region, what will happen? Let's say, look at here. It will behave like this. For example, if this is a fixed boundary condition at this region and a fixed boundary condition in this region, and this is the soil domain that is assigned to it. So the waves will go in this direction, and then it will consider this as a rigid region and reflect back in this direction. Similarly, in this way, these waves will reflect with each other. However, it is not the practical scenario. If you want to avoid this ABC, then it means that you have to consider a very, very, very large soil domain just to distribute those stresses, and that is not possible because you also have to kind of save some computational cost for your analysis. And in order to save the computational cost, the special type of elements are introduced in the STKO as well as in the OpenSees environment, based on the OpenSees environment. So they, what does they do? They absorb the waves and take care of those waves, and it's visible here in the animation as well here. So the acceleration magnitude increase up to 10 g, and it's properly showing us that these are absorbing here, and it is distributed here due to the weight of the building. It is quite visible here. So this is the command line interface you are going to use, and you have to use this information for the analysis. So if you have a 2D boundary condition, right? So a 2D, then you need to specify the thickness because it is a plane strain model. And if you have a 3D, you don't need to define the thickness because you are going to assign it to a 3D domain without wasting any further time. So these are the information that are required. First one is the G, that is the shear modulus, and the second one is the Poisson ratio, and the third one is this region here. So if you are using OpenSeas and you are checking the model, so these are the tags, and these are the nodes definition of the element you have to define, and other information that are required in the analysis. However, at this point, if you define the boundary conditions here for the ABC, then you also need to define the section for the analysis for the consideration of the elements here. And then you, for the other domain, you have to define either concrete or other elements which represent the correct way of modeling the region here. So it's not as simple as it's look like, you have to consider the other definitions along with the definition of the physical properties to regenerate what you are doing. And I will demonstrate this in a very accurate way to consider in the analysis for the proper distribution of the soil waves here. So there will be a practical example on it using OpenSees as well. And I think the best way to consider is first to understand the theoretical background here. So when I mentioned this here as well, that when you are trying to model a soil domain, then you have to define those artificial boundaries conditions here. And if you are using a static analysis, then these are fine. These fixed boundary conditions are fine. However, but in dynamic analysis, the mass wave propagation involved in it, and the outward going propagating radius that I mentions here for those waves, that is shown here in this region. Um, you need to define these artificial boundary conditions. These are the ABCs, because it is almost impractical to define such a large domain to study the behavior of the structure, because uh, it's become very computational costly here. So this is a smart approach here. So that's why we have to adopt the special boundary conditions which are able to absorb the outgoing waves, and it is a in term of spring and dashboard here. There are some interaction modules as well, but those interaction modules does not make any sense here. And if you are using abacus, then in abacus you can use them. This is something we are going to discuss here today. So if you are using abacus, I think you can use the uh, methodology of infinite element. And in order to define the infinite element, you need the editing of the input file, because that is also not possible inside a Abacus file. So you have to generate your file, and then you have to do it with changing some lines in the input file. So while in OpenSeas you already have a complete line of code here, which you can adapt to STKO or manually as well in order to study its behavior here. So the first this element that is implemented by Nielsen for the 2D cases, and then properly extended for the 3D case in the Nielsen as well. And as I mentioned here, if you are using this boundary condition, um, the special absorbing boundary condition, you need some resources for it. So you need the far field element that is required to compute the free field solution in parallel with the main model, right? This is the far field. And you need the dashboard properties. These are the decimal dashboards that's required to absorb the outgoing waves. Don't worry, I will explain these in detail. And then you have to also define the boundary traction transfer from the far field to soil domain, and then the soil domain will consider this to further use in the analysis. So as I mentioned, for the 2D and 3D elements, this is a quadratic 8 node elements and 4 noded elements. uh, these are the node numberings. So you need to be careful about the nomenclature of these elements. For example, if you are using OpenSeas and you have a style domain, then you should be very careful about the nomenclature here. If you look at here, we have this one, two, three, four nomenclature. So you have defined in that manner. for the proper positive Jacobian. However, for 3D, you have to define in this way, right? You have to keep the order properly. And if you are using a 3D notation here, so for 3D notation, you must use this nomenclature here if you are doing the analysis here. So the best way in the STKO environment is to consider your model importing from a third-party software, because it will make it very easy for you instead of working inside the STKO environment. It will be easier for you to consider that. So we have some sort of these combinations. These are B, L, R, BL, BR, and BLRF, right? And K and BL and BR, BF, BK, LF, and so on. So BS for bottom, RS for right, LS for left, BL for bottom left corner, right, and so on. So if you have a style domain, then you have to do this by doing such kind of partitioning that those corners and those all sort of incorporation are considered in this analysis. So what is happening in this model that you are going to consider in your analysis? The first thing that is that if you are using this element, so the element at this point here, at this region, this is the side domain, right? And these are the elements here. So at this point in stage 0, the element X is a fixed boundary condition and it's suitable for the gravity analysis only. If a gravity load G is applied on this model, then it is suitable for it because there is no wave in it. And it stores the reactions at these regions automatically and convert them into the applied boundary forces when switching from stage 0 to stage 1. And on stage 1, this element is then considered as an absorbing element and the reaction of the previous constraint elements are applied as an external force here as well. So the conversion from stage 0 to stage 1 can be done with the set parameter example, which is provided here as well. And the boundary conditions that we are using here, it is very important for the 3D consideration. For 2D, it's a plane strain model, so it's not a big deal. While for 3D, if you are using, so you have some sort of warnings given in the OpenSees command that uh, the boundary conditions should be an extrusion of the main model along with your outward normal here. Look at here at this region. And I have also demonstrated how the extrusion works and how these things works here. Anyways, if you are using the third-party software, you can import them here as well. But the best way to consider is the outward normal direction and those sign notations that are present in it. And other than that, the vertical sides that are given here for the main model should have outward normal, right? And that point either along the global positive x or along the global positive y direction here. So this is x, this is y direction here, and y, and this is z here. And the bottom side of the main model should have normal to the this direction here. So overall, you should be careful about the notation inside the STKO environment. And these are the 3D model sides that are left, right, front, and back may have some natural distortion due to topography, and it is demonstrated here as well. You can see here, as soon as this wave propagate, there is a distortion in this model here. So these are the notations that you should consider in this way for your soil domain, which also represent that if you are modeling the soil structure interaction, you should be careful about this rectangular shape in its notation as well here. So in 3D model, this distortion can slightly deteriorate in z direction because of the deformation. However, it will not affect the result that much. There is a 2D analysis tackle code here as well, which I'm not going to use at this point. However, if you are interested in it, you can click on the link to find the Abacus literature on it. It's a very good literature here, and these are the user elements, the UEL subroutine that are used in the Abacus environment. But for Abacus, you need the Fortran and Visual Studio to be compiled with Abacus in order to use this research paper. So this is about an introduction to the use of the absorbing boundary conditions here, and taking advantage from STKO environment to get benefit from this modeling strategies. Now, after that, I will switch to the ASGA software, concrete models and damage models for the analysis that we are using here. And I will discuss the STKO environment for this as well. Thank you so much for watching.